Again, we examined the terminated transmission line, but this time we're going to describe it not in terms of its input impedance or characteristic impedance or load impedance, but instead in terms of its normalized impedance values, the normalized input impedance, the normalized load impedance, and see the relationship between those normalized values. If we look at the math, do a little algebra, it's easy to determine that the relationship between the normalized input impedance and the normalized input impedance and the normalized load impedance can be written in this form. And again, it's lacking the parameter of characteristic impedance. This is strictly a transformation of a coefficient, a unitless value, ZL prime, to another coefficient, a unitless value, Zn prime. And in this way, is exactly the dual between the reflection coefficient function, which would transform a coefficient gamma L into a coefficient gamma in. Although the impedances rather have been normalized in this case, it really didn't do much to simplify the form of this expression. This expression, like most expressions in microwave engineering, are a bit annoying from the standpoint that it involves things like complex exponentials, trig functions, complex numbers, real numbers, J, things like that. And this is no exception. If we look at this expression, we find this first term in the numerator is going to be complex because the normalized load impedance is complex. The second term is going to be purely imaginary. The first term of the denominator is purely real, and then this second term of the denominator is complex once again. So it's not an easy computation to make, to determine the value of Zn, the normalized input impedance. So the question is there some easier method to calculate this? Now, with computers and calculators and such, it's not quite the profound question it was several decades ago in microwave engineering. Back then, doing calculations involved things like slide rules, and they weren't easy to do. And so engineers back then were looking at oftentimes graphical methods of solving calculations, of determining equations to get answers. So they asked themselves, is there some easier way to evaluate this normalized input impedance? And it turns out there is an easier way. It involves 3 steps, and let's look at those 3 steps. The first step in this process is going to convert the normalized load impedance into its load reflection coefficient value. And we can do that with this equation, the normalized load impedance minus 1 divided by the normalized load impedance plus 1, and that provides the load reflection coefficient gamma L. Once we have gamma L, we can convert gamma L back to gamma in, the reflection coefficient function at the beginning of the transmission line, using our reflection coefficient function. And from that expression, we can determine gamma in terms of gamma L. Then, once we have gamma in, we can convert gamma in back into impedance. Again, the duality here, the conversion between reflection coefficient and normalized impedance. And that expression is provided here, 1 plus gamma in divided by 1 minus gamma in. Of course, gamma in, remember, is a complex value. And the ratio of those two results give us the normalized input impedance. So that's one way of doing this. Again, basically, we're transforming load impedance into load reflection coefficient, transforming the load reflection coefficient using the reflection coefficient function to an input reflection coefficient, and then transforming from the reflection coefficient domain, as it were, back into the normalized input impedance. Now, we look at these 3 equations. We have to do this, and this, and this. 3 mathematical operations. None of them are particularly simple either. They involve complex numbers. They involve complex exponentials. And so you may say, well, this doesn't seem to be much of an improvement. In fact, you could argue it is more complicated than simply calculating the calculating the input impedance, the normalized input impedance function that we provided on the previous page. So why would we recommend this approach? Why would we argue that these three steps are somehow easier? The reason we express this process of transforming normalized load impedance into normalized input impedance in terms of these three steps is that each of those three steps can be graphically accomplished on our Smith chart without having to resort to any calculations at all. And let's see how we might do that. All right, step one. Step one is to convert our normalized load impedance to a load reflection coefficient, transforming an impedance into its corresponding reflection coefficient. Well, that's what the Smith chart does. It takes the entire Cartesian grid of the complex impedance plane and transforms it onto the complex gamma plane, and therefore it effectively transforms every single point in the valid region of the complex impedance plane, the normalized impedance plane, onto the gamma plane. If it transforms every point on the validity region in the normalized impedance to the complex gamma plane, it's going to transfer the point that you care about, the load impedance for this particular problem. So, for example, let's say our load impedance is a value of 0.6 minus J 1.4. Again, this is normalized, so we would multiply this by characteristic impedance Z0 to get the actual value of load impedance in ohms. On the Smith chart, what we're looking for, if we were to transform then this normalized load impedance onto the complex gamma plane, we would find the location of that transformation where this impedance should be on the complex gamma plane by simply identifying two circular contours. The circular contour for a constant resistance of 0.6, all points on the complex impedance plane that have been transformed onto the complex gamma plane, whose real part is 0.6. Then we look for the contour, the circular contour that is labeled x equal to minus 1.4. This is a contour of constant reactance, a capacitive reactance of 1.4. Every point on this contour corresponds to impedance whose imaginary part is equal to minus 1.4. Well, where those two contours cross identifies a point where the impedance is real part is 0.6 and the imaginary part is minus 1.4. That is the example that we are looking for or care about here. In other words, at the point where those two contours cross on our Smith chart, on our complex gamma plane, that is the proper location on the complex gamma plane if we were to transform the load ZL onto gamma L. And that's exactly what that first step is. Transforming ZL into gamma L. We've done that graphically already if we use a Smith chart. So how do we identify these two contours on our Smith chart? Again, we start with a vertical contour on the normalized impedance plane, R equal to 0.6. And when we know when that is mapped onto the complex gamma plane, it maps onto a circular contour on the complex gamma plane. Of course, there's a number of these circular contours that become very small as we approach open circuit or get larger as we move toward the short circuit. We're looking specifically for the circular contour designated as R equal to 0.6. If you look along the Smith chart on the horizontal axis, on the real axis of the complex gamma plane, every time a circle of constant resistance crosses, there is a label, and that label numerically identifies that circle. If we take this point here and we zoom it up, we see it says 0.6. And so the circle that is crossing that point, which is shown in blue, that is the circular contour R equal to 0.6. All the points on the complex impedance plane whose real value is 0.6 when mapped onto then the complex gamma plane. That is the blue circle. Likewise, for the curves, the contours of constant reactance, we look and see there's a scale along the unit circle. And that scale along the unit circle, where the contours intersect with the unit circle, we find there's a number associated with it. And that identifies each of the contours of constant reactance. So if we look down here, we find a number that says 1.4 that is right next to this red contour. And that is the contour of constant reactance that is capacitive. And this is a very subtle but very important point. If we go look at all of these numbers associated with these curves, contours of constant reactance, we'll find that on the upper part of the Smith chart, all of those values are positive. 0.8, 1, 1.64, they're all positive. When we look on the bottom side of the Smith chart, again, looking at where the contours of constant reactance intersect with the unit circle, we find numbers that are likewise positive. To determine which of these is plus and which of these is minus, you have to remember what part of the Smith chart is the inductive region and which part is the capacitive region. The inductive region, if you recall, is the upper half of the complex gamma plane, and therefore the upper half of the Smith chart. All of the reactances in the upper half are positive, and therefore all these contours of constant reactance in the upper half are positive reactances. Conversely, on the bottom half of the complex gamma plane, on the bottom half of the Smith chart, is the region of capacitive reactance in the capacitive region. So all the reactances down here are going to be negative, and that is true then of all of the contours of constant impedance. They are all negative. Even though the label down here says 1.4, we know since it's in the bottom half, the value is actually minus 1.4. Now you may ask, why do Smith chart manufacturers do this? Why don't they label the upper half as positive and the lower half as negative? There is actually a very good reason why they don't, and we'll get to that later. In the meantime, just remember, you have to identify what is the inductive region on the top half, what is the capacitive region on the bottom half, and recognize that the reactances on the bottom half are negative, and therefore these contours of constant reactance on the bottom part of the Smith chart, even though they're labeled as positive, in fact map to a negative reactance. All right, so we've identified our two circles. R is equal to 0.6 is the blue. X equal to minus 1.4 is the red. The important point then is the intersection of those two contours. That is the mapping to the complex gamma plane of an impedance whose real part is 0.6 and whose imaginary part is minus 1.4. That is precisely the load impedance that the example that we are examining here. Take your pencil then and draw a dot at the intersection between the R equal to 0.6 real circle and X equal to minus 1.4, X equal to minus 1.4 imaginary contour. Put a dot there, like this green dot. And notice we label that as our value of ZL, 0.6 minus J, 1.4. But that is not a point on the complex impedance plane. Remember, this is the Smith chart. This is on the complex gamma plane. This is the point on the complex gamma plane where that point, 0.6 minus J, 1.4, on the complex impedance plane has been transformed into the proper location on the complex gamma plane. This is the location on the complex gamma plane on our Smith chart where the transformation from this particular value of load impedance would lie. We are at the correct location. Thus, the first step of our process has been completed. We have successfully transformed the normalized load impedance into the correct value of gamma L. And we did that simply by identifying two contours on the Smith chart and placing a dot with a pencil at the intersection of those two contours. Of course, the question is, what is the value of gamma L? Oftentimes, we don't care. All we know is that the point that we've placed is the correct location on the complex gamma plane for gamma L. If we want to know the value of gamma L, and of course, oftentimes we don't. Remember what we're trying to accomplish here. We're trying to transform the normalized load impedance into the normalized the normalized input impedance. We don't really care what the value of gamma L is explicitly. But let's say we did. Let's say we wanted to know. How would we extract it from our Smith chart? Well, it's fairly simple. The distance from the dot that we made to the origin is the magnitude then of the value gamma L. How would we determine this graphically? Well, we would take a ruler and we'd measure the distance from the center to the unit circle, and then we would measure the distance from the center to our green dot here, as it were, and we would take the ratio. In this case, we would find that the ratio would be 0.685, or 68.5% of the distance from the origin outward to the edge of the unit circle. That is the magnitude of gamma L. How do we determine the phase? Well, remember, we have an outer scale that tells us what the phase of gamma is. This angle of reflection coefficient that we talked about in the outer scale. It's marked directly here. We can simply take a ruler and draw a line between one that crosses through the origin and crosses through our green dot and extend it to when it crosses this reflection coefficient angle scale. And we see that it crosses, here's minus 60, here's minus 70, it crosses about minus 65 degrees. And that is the value then of the reflection coefficient angle. Again, what we're doing is rotating down 65 degrees from the real part of the horizontal axis, of the real axis. And that is the definition then of our angle. So we rotate down to minus 65 degrees. We can use the outer scale to find this value. If we were to go through and do the math, go ahead and insert the value of impedance, 0.6 minus J1.4, into this expression and go through and calculate the value of gamma L. That's exactly the value we would get, 0.685 with a phase of minus 65 degrees. So the point here is that we have located the correct value for gamma L on our complex gamma plane, that of the Smith chart, but we don't necessarily need to figure out exactly what that value is. All we need to know is that we are indeed at the correct spot on the complex gamma plane. Now for step 2, we need to convert this value of gamma L to a value of gamma N, and we use the reflection coefficient function to make that conversion. From the math, we can conclude that what we need to do is take the correct point of the complex gamma plane of gamma L and then rotate in a constant magnitude around the complex gamma plane over an angle of 2 beta L. And then we stop, and then we are at the proper location of gamma N. This is the transformation, the parametric transformation of the reflection coefficient. We did this earlier in the section where we took a specific value of gamma L, and we determined the value of the reflection coefficient at a different location on the line at its input impedance by simply parametrically plotting the reflection coefficient function. But of course the magnitude of the reflection coefficient function is a constant, only the phase changes, and a phase changes proportional to 2 beta L. And so we struck circular arcs over some arc angle of 2 beta L to be able to determine the transformation graphically from one point to the other. Back then, when we were talking about it, we asked the question of why would we want to do this? Why don't we just get a calculator and figure out what gamma N is based on gamma L? Why do this graphically on the complex gamma plane? Well, that's why we were doing it then, is because we're going to do it exactly the same now. And we're going to do it as before on the complex gamma plane. The only difference is a complex gamma plane have all of these impedance, Cartesian impedance contours transformed onto the gamma plane, and thus becomes a Smith chart. But bear in mind, we are doing precisely the same mechanism, the same thing than we did before when we did the parametric plotting of our reflection coefficient gamma z. The important thing, remember, we talked about then was we're moving from the load back toward the input of the transmission line, and therefore our position index z is decreasing as we move down the line to the input. And because z is decreasing, the reflection coefficient angle is decreasing, and when the reflection coefficient angle decreases, we're moving clockwise. And so we are going to take a value, a point on the complex gamma plane, gamma L, and then we're going to rotate clockwise by an angle now that is equal to 2 times beta L, where L is the physical length of our transmission line. We stop at that point, and now we're at the correct value of gamma in. Adding to then our example, where the load impedance is 0.6 minus j 1.4, we're going to say that the line length, the transmission line length here, is 0.307 lambda, about 3/10 of a wavelength slightly. So how do we transform the load reflection coefficient back to the input reflection coefficient? On the complex gamma plane, we simply strike a circular arc moving in a clockwise direction, the circular arc, and the arc angle that we end up with should be 221 degrees, which is equal to 2 times beta L, L being, again, this 0.307 lambda. We stop, and we're in the right location for gamma in on that complex gamma plane. So, how do we know how far to go? We could use the outer scale, the reflection coefficient, and use it to determine a rotation, an arc angle of 221 degrees. But the Smith chart gives us another outer scale in terms of a normalized electrical distance, an electrical distance, I should say, of where we can use then to determine the rotation angle without having to explicitly determine this value of 221 degrees. So let's see how that's done. The slide's a little bit busy, but try to follow along what we're attempting to do. So let's say we take a straight edge and we draw a line from the center, the origin of the complex gamma plane, the center of the Smith chart, through our original value of gamma L, outward to the outer scale. And again, we saw before that it intersects the angle of reflection at minus 65 degrees. Now we could use this same scale and add to that, rotate more around of 221 degrees. Rotate around 221 degrees to this point using this angle of reflection coefficient scale to help us make the determination that we've moved 221 degrees. Generally speaking, that's not how we do this operation, however. Instead, what we look at are the electrical distance scales on the outside. Recall there were 2 of those scales. One scale was wavelength toward load, and the other scale on the further outside was wavelength toward generator. Both of those scales start here on the Smith chart and increase. In the case of wavelengths toward load, 0 to 0.25, back around to 0.5, or a half a wavelength. For wavelengths toward generator, we start at 0, and we go to 0.125, 0.25, a quarter wavelength, 0.375, and then finally back to 0.5. In this condition, at this case, back again. Wavelengths toward generator, therefore, moves in the clockwise direction. Wavelengths toward load move in the counterclockwise direction. And that is exactly what happens as if we were on a transmission line. We move toward the load, increasing z. We move in the counterclockwise direction. If we move away from the load, in this nomenclature we call it toward the generator, toward the source. We assume there'll be a source on the other end of the transmission line. As we move toward the input, toward the source, toward the generator, the index z is decreasing, and therefore the angle is decreasing, and therefore we are moving now in a clockwise direction. So in this case, we're going to use the wavelength toward generator scale. Now we could have used the wavelength toward load. We just have to subtract numbers instead of add them. But since we are moving away from the load toward the generator, let's go ahead and use that outer scale. So we draw a line through our gamma L point to the outer scale, and now we notice that the wavelength toward generator scale has a value of approximately 0.34, or 0.34 lambda. Now, what do we make of this? What does that tell us, this value that is 0.34? Well, it tells us absolutely nothing. Again, hopefully we got that point across when we talked about the outer scale. It's just a marker. It is a mile marker along the interstate. It has no significance at all. But it allows us to go through and determine where we need to stop as we rotate clockwise now around the Smith chart. If I start at 0.34 and I have a line length of 0.307 lambda, what I want to do is start at 0.34, add 0.307 to it, and that is the mile marker then we need to stop. Just like, again, the example on I-70, if I want to go 40 miles further down the road, and I'm at mile marker 23, then I take 23 plus 40, and that tells me I need to continue down the road until I get to mile marker 63. Mile marker 23, mile marker 63, the numbers have no significance. The difference between them is 40 miles. That has significance. That's the distance that we want to continue moving down our line, or down the road. So this is a similar thing here. We want to move up the line toward the generator a distance of 0.307 lambda, because that is the length of the transmission line. We're moving from the load up the line to the generator, to the input. So we start at 0.34 and we add 0.307 to it, and of course we get a value then of 0.647. Here's the problem with that. There is no mile marker 0.647. There is no value on the wavelengths toward generator scale that has a value 0.647, because the maximum value that we have is 0.5. As we continue in this direction, 0.34, 0.39, 0.45, 0.49, and then finally we get to 0.5 and we stop. So what do? We're metaphorically crossing the state line here, and therefore we have to break this procedure of rotating around the Smith chart into two pieces. One is moving from the load down the line until we run into this boundary, and then we continue, once we get on the other side of the boundary, to continue the remainder of the distance down the line. I'm sorry, I always have hard times thinking in mirror image. Remainder of the line down toward the input there. So how do we do this? Well, we start at 0.34 and we rotate clockwise along this index, 0.46, 0.49, and then we get to 0.5. We started at 0.34, we ended at 0.5. That means we have traversed a distance, again, just like our mile marker problem. We take the distance between one mile marker and the other one, the difference between them rather, and that is the distance between the two. 0.5 minus 0.34 is equal to 0.16. That's how far we've moved toward the source, toward the input from our load when we move from this location to this location here. We have traversed down back up the line toward the input of a value of 0.16 lambda. All right, we stop right there. And the question we ask ourselves is, how much further do we have to go? Well, we need to move a value of 0.37 lambda, and we've moved thus far a value of 0.16 lambda. And so what we can do is take the difference between those two, the length that we need to go and the length that we've moved thus far, and we find we need to move an additional value, delta Z2 we call it, of 0.147. How do we move 0.147? Well, we start at this location. Our wavelength toward generator marker is a value of 0, no significance there, but we add a value then, the delta, that we need to move of 0.147. We need to move 0.147 lambda further up the line toward, or back the line, further toward the input. And so we add 0 to 0.147, and of course we get 0.147. That is the electrical index that we need to where we need to stop. So we rotate clockwise. Again, here is 0.1 and 0.12 and 0.14, and then we have to be careful, 0.142, 0.144, 146, and then 147 is right there. And we mark that with a pencil, all right, when we get to that index. So we started right here at 0.34. We moved up a 0.16 lambda to 0.5, and then we started over at 0, and then moved another 0.47 lambda to a value of 0.147 for the marker here. When we add those two values together, we get 0.307, which is the length of our transmission line. All right. So we put a mark here, and now we take our straight edge and we draw a line that starts at the origin, and we go outward to where that mark on our outer scale. It intersects the wavelength toward generator scale at 0.147. The final step of the process is to parametrically plot the reflection coefficient value along our transmission line. We're going to start at gamma L. We're going to take a compass, put the pointy end here at the center and the pencil end at this dot, extend it so it's on the dot, and then strike a circular arc all the way around until you intersect this line that you drew from the center outward to the index of 0.147, and we stop at that point. Now we've rotated the requisite distance, the requisite arc angle of 221 degrees. Notice in this case we didn't have to calculate that angle. We know we've rotated 221 degrees, or the requisite angle, because we've used correctly the outer scale values of normalized distance wavelengths toward generator. So we stop at that point. What is that point? Well, that point is the input reflection coefficient. That is the value of the reflection coefficient function, when evaluated at the input of our transmission line, a transmission line which has a length of 0.307 lambda and a load impedance of 0.6 minus J 1.4. So the point we stop is the value of gamma in, or more specifically, it's the point where we stop is the correct point on the complex gamma plane that corresponds to a value, the correct value of gamma in. If we want to know what that value of gamma in is, we can determine it from the Smith chart. Once again, measuring the distance from the center to that point and comparing it to the distance from the center to the radius of the unit circle. Again, we're going to find it's 0.685 as it was for the load, since, remember, the magnitude is constant with respect to position. With respect to the phase angle of the input reflection coefficient, we simply look at the angle of reflection coefficient scale right here, and we see it crosses at about 70 plus 74 degrees. So we can immediately tell that is the value of the reflection coefficient at the input, and this is at the input. Most of the time we don't care what that value is. Again, our quest is to determine the input impedance, not the input reflection coefficient. Most of the time we don't bother figuring out what this number is. We just know that we are in the correct point, at the correct point rather, on the complex gamma plane for gamma in, whatever the heck it is. We could go through and verify this. We could insert, use our reflection coefficient function and put in the right values, and if we did, we would find we get exactly the value that we inferred from the reflection coefficient, from the Smith chart scales. In other words, we are at the right point on the complex gamma plane. Typically we don't calculate these numbers or measure these numbers. Again, we don't care what they really are. Instead, what we care about is the value of the input impedance. And so we need to finally complete our third step of our process, which is to convert our value of gamma in back into input impedance, normalized input impedance. Mathematically, we could complete this step with this equation. But since we're using the Smith chart, we don't have to do any calculations. It's very simple. When we get through with our parametric plot of the reflection coefficient and we stop at gamma in, to convert gamma in back into impedance, we simply lift our pencil and look to see at what intersection, where does a contour of constant resistance circle intersect with that point, and where does a contour of constant reactance intersect that point. If we look at those two circles, from that we can infer then that input impedance. And so in this case, we see that this circle, the contour of constant resistance, intersects our point where gamma in was, and likewise this contour of constant reactance. So what are those values? Again, we have to identify this circle of constant resistance, and we do that by looking at where it intersects the horizontal axis. A series of values here, and what we see is next to that blue circle is the value of 0.5. That is the real part of our input impedance, the resistive component, the normalized resistive component of our input impedance. Likewise, we see the contour of constant reactance, and we follow it up until it intersects the unit circle, and right where all the contours of constant reactance intersect the unit circle, there is going to be a number next to it, and that number identifies the reactance of that contour of constant reactance. In this case, it's 1.2. The only question we have to ask ourselves, is that a positive 1.2 or is that a negative 1.2? Well, now the value, the point we have, in fact, this entire contour of constant reactance is in the inductive region of the complex gamma plane, the inductive region, the upper region of the Smith chart. So we know that value is going to be inductive. In other words, the reactance is going to be positive, a value of 1.2. Since our green dot lies on the contour of constant resistance 0.5, it must have a resistive value of 0.5. Since it likewise lies on the contour of constant reactance plus 1.2, it must have a reactance of 1.2. We put the pieces together, and the input impedance of this terminated transmission line has a value of 0.5 plus J 1.2. So we're able to get there without really ever having to do any calculations at all. We simply first started by finding the contours of ZL, the real ZL and reactive ZL, on the Smith chart, which maps that impedance to the correct point on the complex gamma plane, and then we rotated around using our compass the requisite arc length based on the outer scale and the knowledge of the electrical length of our transmission line, and then we stopped and picked up our pencil and looked to see where the contour of constant resistance and reactance intersected that point, and that became the input resistance and input reactance. And certainly that is a much simpler process than trying to go through and slug through, certainly on paper, determine the value of that input impedance. Even with a calculator, this is a much simpler process to get the answer.